that I didn't get on there because I had forgot about it for a couple of weeks now, but we'll get that one addressed here. So last week, obviously, was structural engineering. Some of the fun things to think about next week, or hopefully by tomorrow, I'll get a video created for a virtual site visit of our tiny home project so that we can post that so you can see some of the structural pieces with that. So just as a follow-up, is there anybody that had any questions about structural or anything that we need to address or make sure we get to you guys that you either had in your breakout rooms or needed something from us? I can get that on our list. Okay, well, if you do think of something, just send me a quick chat or send me a quick email or something through Slack, and we'll get you what you need for the structural piece. The other thing that we have up there is the scholarship applications. So those are for scholarships during the summer. There's also a camp, but I think it's going to be virtual this year, but I haven't heard a lot about that. You can get some scholarship for that as well. I'm only putting this out there. I looked on the Slack website last night and I didn't see the scholarship applications on there, but they'll be on there soon, if not in the next, by the end of the week. And then they're going to be due by April 9th. We'll just keep that on here so people are reminded. So those people graduating and stuff that may want to apply for those, you can get on that early, because we know spring break will happen somewhere in between there for everybody at some point. So we'll want to make sure people are doing that. The other announcement that I didn't get on this screen here that I wanted to let everybody know is ACE is going to be sending out a full-size drawing of the site. And Kevin, you might have to help me with all the logistics here, but I think they're sending that full-size drawing of the site, as well as some trace paper to do over that to every ACE student.
Yeah, it's going to be, let me see, I have it right here. So it's going to be a full-size base map, a roll of trace paper, some cardstock rulers so that you'll have basically scales made out of cardstock. Yeah, and they've asked if any of the students felt like they needed additional supplies like pens and paper or things like that they just don't have access to in their houses, to reach out to either Sean or I, and we'll try and get gift cards over to you to buy some more stuff like that.
Yeah, so if you can let us know either via private chat here today or right after the meeting if you need that, we want to get that out because I think they're going to try to send that out tomorrow. So if you can let us know if you think you need the extra supplies. If not, you'll be getting all of that stuff for sure in the mail, snail mail as it goes here shortly. So that was the one announcement that I didn't get up there. But any questions on that? Okay. So videos from this week, mechanical, electrical, any questions? Anybody have, how many people, I guess, just show your hands via the chat or put the reactions, wanted to be a mechanical or electrical engineer even before the videos? Is there anybody that was interested in those disciplines? I don't see too many hands. Well, I will let you know that from a construction perspective, mechanical, electrical are two of the biggest components of a building, single components of most buildings that we build. I'm not so sure that's always the same on a bridge or those type of things, but they are very important components to a building, and they're the smarts for the building for sure. And there's something that you don't usually see because they're buried in walls or hidden in mechanical rooms or those type of things. But that's how people want to use their buildings these days, is with the mechanical and electrical systems. So something to always be aware of, and it's something to that everybody touches mechanical, electrical, whether they think they will or not. So, anything else or any thoughts on that? Students or other mentors? Mechanically, electrically? Or we're lucky to have one of our mentors is an electrical engineer. So I will just kind of turn it over to you, Matt, and let you dig in there, and we'll
Thanks,
give them
Sean.
a little bit of more of an overview.
Yeah, thanks, Sean. And this is a pretty broad topic. And I tried to just kind of keep it pretty high level for the short amount of time we have. But if anyone, is interested in talking more details, I could do that at another time or afterwards. It looks like a lot of you guys have done this already, setting the background to an electrical theme. So yeah, I'm going to dive in. Like Sean said, I'm an electrical engineer. Just to give you a little background on my, history is I actually in college I studied more like communications and controls and like that small wire type stuff we'd say. But ever since I've been out of college for almost 20 years now, I've mostly been doing power, and that's broad too. Everything from generating electricity to designing lighting for a room. So everything in between there. So that's kind of been most of my background. I've actually had a lot of experience more on the industrial side. I worked in a refinery for 5 years as a kind of a maintenance electrical engineer. So I've gotten to troubleshoot, large equipment, middle of the night, that type of stuff. And then I've also designed a lot of industrial like plants with, large utilization equipment. And then also have done some architectural buildings, but probably more I'd say on the like commercial side. Right now I'm doing a big transit project in California for an underground train station. The good thing about electrical is the skills transfer pretty easily between the different types of industries. And the same's true for mechanical, I'd say, as well. So yeah, you'll see on the first slide here, what is MEP engineering? So in the architectural world, it's all kind of somewhat lumped together under MEP, which is mechanical, electrical, and plumbing. Typically, the mechanical and plumbing engineers, have a mechanical engineering degree. Typically, there's always some exceptions, but and then the electrical engineers have electrical engineering degree typically. So often in the building world, sometimes there's specialty MEP engineering firms that the architect will sub things out to. If you work for a larger firm like mine, we do everything: architectural, MEP, structural, everything. So just depends on the size of the company and what their market is. So just to touch on some mechanical systems, what a mechanical engineer does. In the building world, a lot of it is the HVAC design, which is the heating, ventilation, and air conditioning. So it's everywhere, everything from exchanging air in rooms to maintaining temperatures. There's also a lot of times there's safety systems like emergency ventilation, and in the cases of fires, and or in case of like depending on the facility, maybe an event where there's like a gas leak or something like that. There might be an emergency ventilation system. There might be steam systems in some industrial type facilities. I'm interfacing with one in a hospital right now that we're working on. There's also like gas systems as well. On industrial projects I've worked, mechanical engineers get involved in some pretty heavy duty stuff like large turbine generators, large compressors, large pumps, things like that for like large process systems. So a lot of different things there. Plumbing systems, in buildings, it'd be like your water systems, wastewater, sumps, which is like you guys in your basements, you might be familiar with having a little sump and a sump pump. So where the water collects at the low points. Drainage systems, just designing the buildings and the areas around the buildings to intentionally drain to the right point so you don't have flooding. And then kind of a niche area of plumbing would be like fire protection and sprinkler systems. That's usually designed kind of by a specialty, engineering firm that does that type of stuff. So
I would add to that,
Yeah.
as far as looks like that's your next thing there is when we typically see a design team created, there's the mechanical engineer that does all the heating and cooling. There's a plumbing engineer that's probably with the same firm, but they work together and tight knit, hand in hand. And then fire protection, those mechanical plumbing engineers will give you some parameters, but then we'll typically have a fire protection contractor that has an engineering background that will run all the pipes and show you where all the pipes and sprinkler heads and do all of that design. So there's actually 3 people typically involved when you're doing that. So it's pretty cool.
Yep. And then just some components that you run into on the mechanical and plumbing side. And I have some pictures we'll go through here, but equipment is like pumps, which, pump liquid, basically pump a certain whatever flow rate you need, and they also will increase the pressure of the liquid. Compressors are pretty much the same thing, but with gas or air, is flowing gas or air through a pipe or a system and increasing the pressure. Fans are for blowing air. In the HVAC systems, you have a lot of fans. So that's like I would say that's a lot of your major equipment. Then in order to transmit the fluids or the air, you have piping for the water, piping for your whatever other liquids you have. You have duct work in buildings where all the air flows from the HVAC systems. And then you have valves and dampers typically. So valves would be to basically close off or shut off the liquid flow in the piping system. And then a damper would be kind of the equivalent in a mechanical system to it would open and close to stop the airflow. And there's a lot of different, within all these things, there's a lot of different, items. Like with dampers, there's depending on, there's different codes with, you have to have fire dampers and fire smoke dampers and all kinds of stuff like that as you get into the details. So
your next screen is there. I think one of the things that we kind of didn't mention, but there's a specialty discipline called process engineering, which uses a mechanical engineer, a plumbing engineer, and a mechanical process or a manufacturing process, and they try to engineer that process so it could be more automated. One of the projects that I worked on is they took raw material, ground it into a powder, added water and chemicals to it, and then they put it in a spray dryer, which dried out that material again so that they could go reuse it. Well, the process engineer figured out how that process went from A to B to C to D. And then the mechanical engineers had to size the pipes and put the valves in the right spot so that they could add water and add liquids and all that kind of stuff. So if you're interested in that, it's a really cool thing, especially these days as manufacturing plants which used to be very manually operated, and people can't find people these days. So they're starting to make them more automated. So the process engineers are becoming more important because you're taking a manual process and trying to make it automated. This is what I worked on. So it's really cool if there's anybody that's interested in that. So
yeah, and I've done a lot of work like in the oil and gas business, and also in the like the petrochemical industry and like pharmaceuticals. Often it's a chemical engineering background who is the process engineer, and what they do is, you can think of it as like everything inside the pipe. They're figuring out all the magic behind that, and then the mechanical guys kind of take it from there to spec out the equipment for that. So yeah, often the process guys are kind of a little bit more specialized in their specific industry, I'd say.
yeah, for sure.
But yeah, it's a pretty neat, yeah, it's a good field as well. So so this is just a kind of a photo. I actually grabbed it from one of our my company's marketing brochures, but this just shows you this. Now this is not a tiny home, obviously, but this is a this shows you a large HVAC system with, you know, these are all fans here, and this is all the duct work connected for like a large HVAC system. So you know, what you got here is you got fans here that are blowing the airs through these ducts. So that just gives you an idea of the scale of some of this stuff. And then this is a picture that I actually took of a similar site of a underground train station that I'm working on. And this is a emergency ventilation fan. And just to give you guys, this is a very large fan here. Like this is probably about 6 feet high, tall here. So, you know, this is a very large fan for emergency ventilation in the event of a fire in this underground station, you know, which is enclosed, obviously. So, you know, this is actually the dampers on, you know, the input and output sides here. It's just showing you how it's sucking the air through and blowing it out, you know, the other side. So kind of an interesting thing there. This shows, you know, this is the motor here in the middle, and you can kind of see like these are the some of the controls that come in. So that's just another example of like a large fan. Plumbing systems. This is like just a kind of a tie-in to a water, like a, you know, regular water system here. You know, so this just gives you an example of this is just simple piping. These are connection. This is called a flange, which is a connection where you kind of have this flat face here, and there's a gasket in between, and it's bolted together. That's just one of the methods of connecting piping together. You actually could see down here, it looks like there's some screwed connections as well down here. And then this is a valve, what we talked about. So this is what you would, you'd rotate this handle to open the valve to allow water to flow, and then close the valve to block off the water here. So, and then this is actually this is a fire water system here that's connected in, that has these are also these look like they're shut off valves basically for a fire water system here.
Maybe anybody guess why the fire protection pipes look so much bigger? Anybody? Have a rough idea?
Did they have to take more water, like be able to hold more water? I don't know.
Yeah, that's partly what they're trying to do. You got to get that water distributed to all the fire protection heads, and depending on the specifications of the system, you got to get it there really fast, and they'll just flood the system. So typically fire protection pipes are very large starting out, and then they obviously go down to the little sprinkler pipes. But It's getting enough flow to your sprinklers so that sprinklers can put out the fire is a lot of what they're doing. So.
Right. This is actually a picture of my basement, just to give you an idea of the scale we're looking at for the tiny homes. But in your house, it's more along the lines of, you have a hot water heater here, got a small HVAC system here. This is a humidifier that's on it. That's adds a little humidity to the system. This is the ductwork you'll see inside your house. So, typically, I probably won't get into, too much, detail on, all the calculations today and stuff, but for things like residential type systems, generally there's some rules of thumbs, like, depending on square footages of homes, then that's how you get certain sizes of air conditioning units and certain sizes of, hot water heaters, which is all based on, engineering calculations that are done for any type of system. But, obviously for residential, things are a little bit more cookie cutter. So you can kind of, use some typical rules of thumbs for stuff like that. So let's see here. And then, so that was the mechanical side. I'll talk a little bit about electrical, which is different, but there's a lot of parallels, which I'll kind of get into. But just electrical engineering in general, like if you guys decide to go to college and major in electrical engineering, it's very broad. I mean, it covers, power, control, communications, signal processing, electronics, robotics, like all kinds of stuff. And generally the first couple of years in school are kind of covering the basics, like very heavy math, all your physics classes, stuff like that. And then usually the last couple of years of your undergrad, you kind of pick a area to specialize in, whether that's power or controls or whatever. And then you'll get a job and it might be different. So, but that's the reality of it. It's a very broad field, and typically some of them, like the MEP type stuff, generally bachelor's degree is kind of all you really would need, I'd say. But sometimes, like some of the other areas are really specialized, like some of the technology jobs and electronics and, designing computer chips and things like that generally require more, advanced degree if you wanted to go that route. So, and like I mentioned, in the architectural, like MEP world, it's mostly power distribution and lighting design. So, figuring out how to get power to whatever devices need power, and then, lighting up the building or the outside area that you're designing. So, and since we're kind of on the more looking at the building side, also want to give you guys a little bit of background on, typically, what we do is we tie into a utility somehow, and this kind of, gives you an overview of how that works. So generally, there's a generation station somewhere that's going to have it could be a various sources of power. We used to have a lot of coal, and that's kind of going away. So we have a lot of natural gas power generation. There's some nuclear generation, not a lot in the US really, but there's still a little bit. You're seeing there's some hydro, like on rivers and things like that, using the water as a motive force for a generator. And more you're starting to see a lot of renewables. Solar is getting a lot more economical, and we're seeing a lot more of that. Wind power, you're seeing a lot more of that as well. So that's your generation source. And often nowadays too, you're seeing a lot of distributed generation on facilities. And we'll touch on that a little bit with sustainability side, but you know, you're starting to see a lot more solar, like even at the residential users, and we'll talk a little bit about that for the tiny homes, just because the, you know, cost of those is relatively low these days. So you're starting to see a lot more of that. Also, microgrid systems, just with, you know, local generators at sites and things like that as well. So, but then, you know, on a utility scale, typically you'll have a, you know, generation station. You'll have something called a power transformer, and I'll get into that a little bit. That'll, you know, step up the voltage to a really high level for transmission. And I'll kind of touch on why that's a good idea for transmission. And then you'll kind of, as you go through the system, you'll start stepping that voltage down, you know, to distribution levels, and then, you know, down to the level that it comes into your home, which would, you know, typically the 240/120 volt level. And for a lot of the commercial and industrial, it's the 480 volt level. So I'll kind of get into this a little bit more. These are just a little bit more. Yeah, go ahead.
For a sec, yeah. Just how far down that line do you get sort of being more involved with buildings? And then also, I don't know if you have any info, but just kind of curious, like what's going on in Texas, like where is the failure happening that's causing people not to get power to their houses, if you have any.
So yeah, it's interesting too. It depends on whose postings you read on social media, but there's and I think there's a little bit of truth to some of all. Well, one, and so Texas is kind of unique in that it's not interconnected with the grid that most of the rest of the US is connected to, because in Texas, they've decided they didn't want to follow, you know, all the federal, you know, regulations. So they're in an unprecedented, you know, cold snap, which, you know, it's kind of crazy. Even in Dallas, it dipped below zero for like 2 days or something, which is just unheard of. So the demand for power there has really exceeded their capacity. And they're not interconnected with the rest of the grid. So if they were, yeah, it wouldn't have really been an issue. I don't think. So I think that's the main issue. And then you'll see the anti green energy people on social media are saying, oh, it's because they've tried to have a bunch of windmills and they're all frozen now. And they showed some pictures of that, and there is a little bit of truth to that. You know, there's definitely, every form of energy has upsides and downsides. So, you know, you could definitely see it. I saw some people with even the EIA, which is the government energy agency, will show you like over the past month, the energy demand in Texas and where the sources came from. And you'll see that the renewable amount supplying the power is less now than it was like 2 weeks ago, because a lot of that was down, but it's still a really small percentage of the actual power source there. So you've seen natural gas production go up. So yeah, it's kind of a combination of both, I think. But the biggest thing is probably just that they're kind of on an island from the rest of the grid. So yeah, that's interesting. That's been a hot topic of discussion this week. So
I think it's fun because it's connected so closely to what we do. I mean,
it is, yeah. But like, and it's interesting, like when I worked in the refinery, we actually had cogeneration there, which basically meant we took, so I worked at it was a plant that we used about 80 megawatts of power. And to put that into perspective, you know, your house is like more like 1 kilowatt, you know, so it's very small, you know, it's a much larger scale. So we actually generated on site enough power to power the whole plant, just from waste heat, basically. So, you know, we use heat recovery to actually run generators to produce power, but we stayed connected to the grid to export power. And, that's one thing on the industrial side you can do is you can export power to the grid. Even residential, you can export power, but they typically don't really pay you a good rate for that. Best case you're going to ever get for that is what they call avoided generation costs. So just like the base cost that it would be for them. So I mean, say, I don't know, say they might pay you like 1 cent a kilowatt hour, but you're paying 10 cents or so from the utility, something like that. So yeah, it's kind of interesting. Yeah, but like in a refinery like that, you typically would actually take I don't know, can you guys see my cursor on the screen or no?
Yeah, we can see it.
So you would typically actually take a service right from a transmission system in a big, huge industrial facility. And so you would be at this level basically. And then obviously if you're designing a power plant, you'd be doing this and stepping it up to the transmission. But typically for like a building, like a commercial building would probably be, more at this level where you're either taking the 480 volt in, from the utility, or you're maybe taking in the like 12 to 15 kV service. And then just, if it's a large commercial like place, you'd have maybe a handful of transformers to go like 12 kV down to 480, something like that. So that's for those types, or like a, manufacturing facility or something like that. So yeah, it really just depends on the needs and how much power you need. So, but typically obviously the more power, obviously the cost goes up a lot, residential, they're not really, they're pretty much just charging you for what you use energy wise. But when you get up into these bigger needs, they actually sometimes have to upgrade their whole system just to give you enough power. And that's when it's going to cost you a lot, basically. So, yeah, so this is an area too where there are engineering firms too that really just focus on serving like utility customers, and they really get into the details of this. Or you could even work for a utility as an engineer as well. So, might get boring though, but.
Well, Excel must never be bored because they're
yeah,
always busy.
Yeah. So yeah, so like I said here, these are kind of the different voltages you'll see, and I'll get into that a little bit shortly here, what that means. And then I mentioned transformers on the power system. That's kind of a big component that is used to raise and lower voltages. And these are different types. I mean, even your little iPhone charger or whatever, the reason it's a block is because it has a little transformer in it, basically. What you're gonna see for residential, like for the tiny homes, I think from what we saw, it's probably gonna be something like this for the pole mounted transformer. And then so that would, in areas that are all underground, it'd be something like this, a little pad mounted green transformer. So yeah, if you guys go out in your neighborhood, you're either going to see these, if you have underground distribution, you're going to see these out in the neighborhood, or you're going to see these pole mounted little transformers. And that's how you guys basically, you take it from there and bring it into your house. So this is a transmission station, switch yard, where it's, probably taking 138 kV and stepping it down to like 35 kV or something like that. So, all right, so some concepts, and you guys, I mean, some of you have probably taken maybe like one physics class, some of you haven't, but there's some important concepts that actually apply to mechanical, electrical, and plumbing, across the board. So the first one I'm going to go through is flow rate in the mechanical world, and it would be called current in the electrical world. So, for electrical, it's actually the flow of an electric charge through a medium, which typically is a wire, you know, in electricity. And what that's commonly referred to is the amp. It's an ampere, but typically you'll see that called out in amps. So that's the electrical. So that's the rate of flow. And in the mechanical world, it's the volumetric flow rate, which is you know, the volume of fluid. So like cubic meters per second or cubic feet per second. That's usually what you'll see for you'll definitely see like cubic feet per second, or you know, standard cubic feet per minute, or units like that for airflow. For liquids, you'll often see like gallons per minute, or you know, barrels per day, or something like that. So, but basically the same concept for mechanical and electrical. So that would be the rate of something flowing. So, and then this kind of gives you a picture of this. So in the mechanical world, and Sean touched on this a little bit with the fire water system. So if you need more water to flow, what do you do? Anybody?
You make the pipes bigger.
You make the pipes bigger, right? So you need more water to flow. You make the pipes bigger, right? So for electrical, you need more current to flow. You need more amps. What do you do?
You make it bigger.
Make it bigger. See,
Yep.
it's so simple.
Bigger wires.
Yeah, so
More
it's
copper.
pretty, yeah, I mean, and that is one area where it's, at least conceptually, now the exact equations and all that are different, but yeah, if you need more water to flow, you need more air to flow, you make the pipe bigger, you make the ductwork bigger. You need more current to flow in electrical, you make the wire bigger. So that's pretty simple. So, okay, so that's an important concept. The next one is pressure in the mechanical world, which is same thing as voltage in the electrical world. So, so conceptually speaking, you know, pressure, if you took physics, you know, it's the force, you know, over the area of the walls, basically. Does anyone have a pressure cooker, like an Instant Pot? Yeah. So what happens when you release the pressure after it's done?
Like a bunch of steam escapes from the top, and it's like kind of gnarly.
Yeah, it is kind of crazy, huh? Yeah. So yeah. So the higher the pressure is in a, you know, the more it's going to explode, essentially. So, you know, and voltage in electrical is actually the same concept. It's the electrical pressure, basically. You know, and as you get to higher voltages, you know, you don't even have to touch the wire. It's gonna, you know, jump out and get you, actually. Just like Kevin has behind him electrical arc showing on his background. It's yeah, so like as you get to higher, you know, voltages, it's gonna jump out and get you. So so think of it this way. Okay, so if I have more pressure mechanically, what do I have to do with the pipe?
Make it
Make
bigger.
it smaller.
Make it thicker.
Thicker, yeah. So exactly. So if you have a higher, you know, higher pressure, you need that pipe to have a thicker wall, right? So it doesn't burst. And then for electrical, more voltage, what would that require?
Thicker. Wires.
thicker insulation. So, or something with a better insulating material. But yeah, exactly. So you'll see that if you ever look at like higher voltage wires or higher pressure rated pipes, they have a thicker, thicker wall or a thicker insulation for the wires. So keep that in mind. All right, and then this concept here, as we evaluate these systems, whether they be mechanical or electrical, there's a concept that always comes into play. Pressure drop through the system, and which is resistance in the electrical world. So that's a opposition of current through a wire, or like the frictional forces in a mechanical system. So what that is like this just shows kind of an example of, in the mechanical world, if you have like you can think of this as like you guys have been out in your yard and you're using your hose. What happens when there's a little kink in the hose?
Not as much water.
Right. So that's what. So this is shown a little. They have a little orifice in here, which when you put a restriction in a line, like if you kink the hose, it's not going to come out as fast, and as high of a pressure as it did before you had that kink there. So that's an important thing to consider in these systems. And then same deal in electrical systems. And you'll see, like, when you start getting into these, even when you don't have an actual kink in the hose or an actual resistor, just by having those pipes long or the wire long, it's still going to have resistance, more and more resistance as the lengths get longer. So that's something that comes into play. On HVAC systems, it actually is a really big deal, because with air, you're looking at like very small, pressure type systems. So even the smallest, tiniest drop in pressure is a big deal. So something to keep in mind there.
Yeah, and I'm assuming it's the same in your world, Matt, but you always want the end to know what the pressure is at the end, because that's probably the most important part. Like, just think about your house. If they didn't have good pressure, or maybe your house doesn't have good pressure at the sink, you can't wash your hands as easily, those type of things. So
Right.
everybody's
And
got to
actually,
think about what the end use is.
and that's actually why for electrical, why these transmission lines, they're typically really long, like hundreds of miles, say. Those run at a higher voltage, because the concept I'll get to in a second here is power. So power, if you've taken physics, it's work over time, and which is tough to equate to in engineering world, but it's really the force of something. So we talked earlier about what was the force inside a pipe pressing out. Starts with a P. Pressure, right? And then we talked about, and then there's velocity, and it's you can kind of think of velocity like just like flow and or current. So you have this power is, power in the mechanical world is proportional to the pressure and the flow rate. In the electrical world, it's proportional to the voltage times the current. Actually, in electrical, it's really easy. It is the voltage times the current, essentially. So as you're sending power across a transmission system, what the transformer does is it raises or lowers the voltage. So if I raise the voltage, so say I'm transmitting a constant amount of power, if I raise the voltage, what's going to happen to the current? If P is the same,
The current's gonna go down.
Correct, correct. And then, so another thing too is that um, there's a couple advantages to that. One is if the current's lower, you can use a smaller wire to transmit the same amount of power. And then also if the current's lower, you don't have those drops, those voltage drops, or in the fluid world to be the pressure drops. So that's where transmitting is always good at higher voltage or higher pressure. But then once you get down to the user, it's safer to have things at the lower voltage, basically. Does that make sense? So in these MEP systems though, which will often the relationship between the mechanical and the electrical engineer is, so the mechanical engineer or the plumbing engineer will go through, design their systems, design the water flow rates, design the airflow rates, design the tons of cooling capacity, things like that. And then, specify the fan sizes they need, the air conditioning sizes they need. And that's basically, they're really defining the power requirements. And then the electrical engineer will take those power requirements for the fans, the pumps, all that, and then design the electrical system to feed those, feed that equipment, basically. So that's generally how the interaction goes. So usually the electrical engineer is kind of behind in the schedule where the mechanical and the plumbing engineer is. So that's just how that interaction happens. And then just one other concept here is just energy that you guys will see with, especially with electrical. It's no, that's how we pay for the power, usage. It's basically just power times time, essentially. So if you use 1 kilowatt for an hour, that's 1 kilowatt hour, basically, and that's how you get billed. If you use 1 kilowatt for 2 hours, it's 2 kilowatt hours. So. And I talked a little bit about transformers already, but this kind of it doesn't really look like this transformer, but it basically converts power from higher voltages, lower current to lower voltages and higher currents. So that's what transformers are doing. The P stays relatively constant, other than a little bit of heat loss, which is pretty minor typically. Other electrical considerations, there's a lot more details you got to do here, and I didn't really get into three-phase versus single-phase power, but three-phase is usually how generators work, and what we have at commercial and industrial facilities versus single-phase and residential. You have to consider the incoming voltage, which we touched on a little bit. Designing lighting systems, receptacles, which in households, that's really mostly what you're doing, other than appliances, is the lighting systems and receptacles. Grounding, which is an important safety thing, where you want to make sure everything that's not carrying the electrical, the hot leg of the current is actually grounded so that people don't get shocked. So you have grounding systems in buildings, which are eventually connected to the earth through like ground rods or other systems. Backup power systems, often depending on the type of facility, you might have a backup generator, or you might have solar system or something like that. In some areas, you might have surge protection, which protects from like voltage spikes, or lightning protection in areas where there's a lot of lightning. And then there's a lot of code requirements. Once you get into industry, they actually don't teach you any of this in college, but you spend a lot of your time just learning the codes. And like the National Electric Code is a major one, especially for building projects. There's often local codes you have to learn for wherever the project is you're working on. And there's also energy codes as well, which you see these popping up more and more. It's really big in California, where for mechanical and electrical systems, where they're really looking at energy efficiency and making sure you're using as little power as possible. So I talked a little bit about this MEP workflow. You know, typically you'll have mechanical HVAC systems designed for appropriate airflow, heating, cooling, equipment and ducting size, and then same thing for plumbing. And then electrical systems are designed based on the requirements for those systems, and then other electrical requirements such as lighting and receptacles. And then the electrical engineer that calculates that total electrical load to size the incoming utility. I'll touch a little bit on sustainability, you know, which is like energy efficiency is a big thing here. And this is something that some of these local energy codes enforce, having like very high efficiency equipment that doesn't lose a lot of heat. One thing that's pretty standard these days. It really evolved quickly just in the last like 10 years or so, but LED lighting is pretty much standard now everywhere. But you know, that's brought a huge efficiency, you know, energy savings. Heat recovery, I kind of touched on that earlier. There are some industrial facilities and, you know, processes that have a lot of you know, heat loss through various pieces of equipment they have, and if they can capture that heat and either, you know, run a generator to generate power, or, you know, heat, use it for like heating water, things like that, that's a good way to be efficient. There's like sophisticated lighting control systems, and even like, you know, motion sensors when you go into rooms, things like that, for lighting controls that help save energy. A lot more renewable energy sources coming on board as well. So one thing that I
was just going to say,
yeah, go ahead.
Go ahead. I was going to say one thing from a mechanical perspective. Most of these deal with the electrical perspective, but the mechanical perspective, they're looking at geothermal and some of those other resources that are sustainable. You're using the earth or the constant temperature of the earth to heat or cool your facility. And those are other ones. They're just not quite as popular because they're not as cost effective, depending on where you are in the country or even the town. So that's another one that's out there that people use.
Yep. And then this just has this couple pictures here of, you know, some, you know, solar panels on houses, which you guys have probably seen a lot now. That's getting very economical. Wind farms, which personally, wind's not something I'm most sold on, but that's another. And then the below just shows kind of an example of you know, heat recovery system where you know, they have basically a generator. This is like a gas powered power generator that produces electricity, and those actually have a lot of heat that comes off of them. So, you know, you could pipe that into a heat recovery system, you know, heat up hot water or steam. So that's a good way to use, you know, some of those things. So,
and I think some others
not,
is,
yeah.
Go ahead, Matt.
I was gonna say probably not in the tiny homes though.
Yeah, I was going to say some of the other sustainable things that are related to plumbing and mechanical on the other side. These ones are the easy ones for the electrical, but the low use water, like low use water fixtures. So when you turn on your sink, you're not using as many gallons per minute, those type of things. Those are ways to save energy or save water in that instance. Many jurisdictions have a non-potable water source. that you can use or gets piped around the site where you can use that to sprinkle the lawn or water your landscaping with non-potable water, which just means it hasn't been through the wastewater treatment plant. But it's still safe to put on the ground. It's probably rainwater or something like that. So a lot of the mechanical type stuff is because of water, saving water, and then energy wise, just having really high efficient mechanical systems. They're getting more efficient, so they don't use as much electricity or gas or whatever it is. That's how you become more sustainable on those systems as well.
Yep. Any questions? Yeah, oh wait, is that Eli? Looks like you're talking or no? Oh, sorry.
That's okay. You can be on
No, it's
screen.
fine.
We don't mind you being on screen.
Yeah, no, just give me a shout if you guys got any other questions. Even if it's just like, you know, typical day in the life type stuff, I could talk to you guys about that. So
Let's see. Okay. So I think that was awesome, Matt. Thanks for doing that. It gives everybody an idea of where their electricity comes from if they don't they don't know already, as well as the mechanical and electrical systems. So obviously tiny homes are a little bit different, a little bit smaller scale. There's two components within the RFP. And I don't know if it says it here, but I did send everybody the RFP, so they've got it. But there's two components. So you're going to have the tiny homes as part of your project, and then you're going to have the community center, also part of your project. You could call it a clubhouse, you can call it a community center. It's hopefully a place where people within the tiny home community can go and use and those type of things. So I think as you guys are starting to think through your design and all those type of things, what are some of the ideas that you can use or that you might want to weave into your story about your design, where it's headed? I don't think you necessarily